Hello. Today we are going to go over how to do bending moment diagram very quick. So let's get started with a simple question first. So let's say we have a beam. It's just similarly supported, and then we have a load in the middle with a value of P. So the first thing we need to find is the reaction force on both ends. So let's call this point A and this point B. So we will have a reaction force P over 2 on both sides, right? So, and then we can draw the shear diagram. Yeah, we can. And then, so it starts at P over 2 going up. So this is P over 2, and then it goes straight until it reached the middle. So as we can see, there's a force P pulling down. So the line dropped with a value of P. So if it is P over 2 and then minus P over 2 minus P, then it becomes negative P over 2, right? So this becomes negative P over 2. And then so you just because you do not have any other force as you move along, then it stays constant. So in the end, it goes back to 0 because there is a reaction force P over 2 on the right hand, on the reaction point on the support. So this is like come back to 0. So this is your V diagram, and then the moment diagram is actually very simple. So let's say this is the moment diagram, and then we know that the open-ended beam could not support any moment. So we know that the reaction support A, the bending moment is 0. So it starts at 0, and then it increases linearly because moment diagram is just the integral of this shear diagram. So the shear diagram is a horizontal line. Then if you take the area, then it just becomes a linear function, right? So it goes up like this, and then this value is just this area here. So let's call this L, and this is L. So this is just PL over 2, right? So this point is PL over 2, and now after we pass the middle point, then we are summing out a negative area. So we have so it becomes decreasing. It goes back to 0 because this area is also PL over 2, but it is negative. So PL over 2 minus PL over 2, it just comes back to 0. So this is a simple case. So yeah, so we are just going to talk about this really quick. So now let's move on to one more complicated problem. So let's say we have a distributed load. So let's see, we have two support, and then it is distributed load only in the right part of the beam, and the concentration is Q. So the first thing we need to do is to find out the reaction force on both sides. So to do that, we can sum the moment about one point. So let's say we are summing the moment at point B. Then we have, let's say this is L over 2, and this is L over 2. So Q is like rotating counterclockwise, right? So it's positive. So it's Q L over 2 times the centroid distance L over 4, and then reaction force at point A is rotating the bar clockwise, so it's negative, so it's minus. Let's call it RA, RB. So minus RA times L equal to 0. So to solve this equation, we have RA is equal to 18 QL. So once we find RA, it's really easy to find RB, right? So RB is just equal to Q times L over 2 minus 18 QL. So with that, we find RB equal to 38 QL. So once we have found the reaction force along the beam, then we can draw the shear and bending moment diagram really quick. So let's try it. So we know that this is 18 QL, this is 38 QL, and this is Q. This is L over 2, L over 2. Okay, so let's draw the shear moment diagram really quick. So we know that it starts at 1A, right? So I'm just going to normalize the axis by dividing by QL. So this is 1A. It is 1A like across until it meet a distributed force Q. So Q is the distribution of the Q is linear. So the shear force is like varies linearly. So it decreases with a slope of 1, and then this is like 1/2 away, so it becomes 1/8 minus 1/2, so it becomes 3/8. So we know it ends at negative 3/8, right? 1/8 minus 1/2 is negative 3/8. So we know that it ends at negative 3/8. Like somewhere here. Then that's our graph. So there's also one more thing that we need to do. We need to find this point here. So let's say this is 1/8, and then this slope is 1. Then we know then this distance is 1/8, right? So this point is 5/8L, and then now let's draw the moment diagram. So let's say this is our moment diagram. Let me change color here. So it starts at 0 because these two endpoints could not support any moment. So it starts at 0, and then it increases linearly to a value. So in order to find the value, we need to find the area of this rectangle. So the height is 1/8, the length is 1/2. So moment diagram. I will just normalize everything by dividing by QL squared. So 1/8 times 1/2, so it's 1/16. And then it still goes out until it hits like 5/8, right? So this area here is 1/8 times 1/8 times 1/2, so it's it is 64 times 2, 124, 128. So it reached a maximum point at L equal to 5AL with a value of 160 plus 128, 1 times 128. That's the number we put in here, and then it goes down to some value here. So we need to find the area here, and this area is just 3/8 times this distance 3 times 3/8 and then times 1/2. So that gave us 128.9. So it decreases with the value of this number here, and then so it should go back to 0. There is also one more thing to pay attention here. So as we can see at distance L equal to 5AL, the shear is 0, which means the slope in this curve is 0. So we should draw it like a parabola with a slope of 0. So that's how we. So with that, we have finished the question. Thank you so much for listening. If you have any questions, please feel free to email me.